Today we are starting our unit on graph theory. So to start, the birth of graph theory goes back to 1736 when mathematician Leonhard Euler, who lived during the 1700s, came passing through the town of Königsberg. Königsberg was divided by a river into 4 separate sections, which were connected to each other by 7 bridges. The question posed to Euler was, is it possible for a person to take a walk around town and cross each of the 7 bridges exactly once? This was a thought that people in the town had had, and they honestly wondered if it was possible. So the theme of this unit is to figure out how to create efficient routes along the streets of a city, town, or neighborhood for the delivery of goods and services, such as police patrols, garbage collection, mail delivery, newspaper delivery, pizza delivery, etc. These types of management science problems are called Euler Circuit problems, and these are actual logistical situations that honestly use graph theory to be more efficient. So, to start with, Euler circuit problems have a few characteristics. They are generally routing problems, so problems that are concerned with finding ways to route the delivery of goods or services to an assortment of destinations. The goods or services could be packages, mail, newspapers, pizza, garbage collection, bus services, etc. The destinations could be homes, warehouses, distribution centers, terminals, etc. So one example would be the Amazon delivery guy trying to figure out the most efficient route to deliver all of his packages. He doesn't want to have to retrace his steps as he's delivering because that costs the company more in gas for the truck. So there are 2 questions to ask yourself. First, you need to ask, is an actual route possible? We'll talk more about this in a minute, but an Euler circuit involves taking all possible paths exactly once and ending where you started. So, is that route actually possible? And second, if it is possible, what is the optimal route? So it depends on what your problem is looking at. Are you trying to minimize cost, minimize distance, minimize time? What is it that you are most concerned about as you are creating your route? So Euler circuit problems answer both the existence and optimization question. So for an Euler circuit, every street or bridge or lane or highway or whatever you're talking about within a defined area must be covered by the route. And they are covered exactly once. So, we'll come back to the applications. We're going to look at just the basics of graph theory for a few minutes. This diagram here is an example of a graph. Graphs include vertices, which are the points. So the vertices in this graph are the points A, B, C, D, E, and F. The edges are all of these lines connecting the vertices. So for edges, you would label them like you did in geometry. So we have the edge AB. There is a line that connects A to B. We also have AD. Then we have this loop here where B is connected to itself. We have BC as an edge. We have BE as an edge. Then if I look at the edges that start at C, I have 2 edges that go to D. So I actually have two CD edges. And then my last edge is DE. You can write them in any order. I think it's most efficient to go in alphabetical order to make sure that you don't miss any edges. Now, if you're using formal notation, your vertex set means you're writing it in set notation with curly brackets. You would say your vertices are the points A, B, C, D, E, and F. Similarly, your edge set, we would say your edges include AB, AD, BB, BC, BE, CD, CD, and DE. Now, we have a couple special situations here. An isolated vertex is one like point F, where it has no edges that go to it. Then multiple edges are this situation that we have here with CD. There are two edges that go between vertex C and vertex D. So we said that there is a multiple edge at CD. Now, the whole point of a graph is to define pairwise relationships within a set of objects. The objects are the vertices, and the relationships are the edges. So x is related to y if and only if xy is an edge. You could use this to represent friendships. You could use this to represent business relationships. You could use this to represent physical paths so that you are walking or driving. So it does not matter what shape the edges and vertices are in. It only matters which things are connected to each other. So all three of these diagrams are technically the same graph, because if you look in the first one, they're all in a nice straight line. You go A to B, B to C, C to D. That's it. Well, the second one is the same thing. If you start at A, the only edge going from A goes to B. And then if you continue on the path, you go B to C, and then C to D, and you're done. Same thing with the third one. If you start at A, you go A to B, B to C, C to D. They just folded the first diagram into different arrangements, but they represent the exact same set of relationships. Now, we are going to look at some more advanced vocabulary, and all of our vocabulary words are going to refer to this graph here. So, adjacent vertices. Adjacent means next to. So two vertices are said to be adjacent if there is an edge joining them. So for example, G and F are adjacent vertices. B and E are adjacent vertices. However, A and E are not adjacent vertices because there is no edge from A to E. Similarly, we have adjacent edges. Two edges are adjacent if they share a common vertex. So GF and HF are adjacent edges because they share the vertex F. AB and AC are adjacent edges because they share the vertex A. However, ED and AB are not adjacent edges because they do not share a vertex. Now, the next one is very important because it will be used in quite a few theorems that we talk about throughout this unit. The degree of a vertex is the number of edges at that vertex. If there is a loop, so here at E we have a loop, the loop contributes twice toward the degree because the beginning and end of that edge are at E. So let's go through. If we look at the degree of A, at A we have 3 edges. So the degree of A is 3. If we look at B, we have 1, 2, 3, 4, 5 edges at B. C, we have 1, 2, 3. D has 2 edges. E has 4 edges, because remember you have to count the loop twice. F has 3 edges. G only has 1 edge, and H only has 1 edge. So those are the degrees of all of the vertices. Now, continuing with the same diagram, odd and even vertices. An odd vertex is a vertex with odd degree. An even vertex is a vertex with even degree. And again, whether a vertex is odd or even will be referenced in several theorems that we talk about in this unit. So in this diagram, how many even vertices did we have? And how many odd vertices? Even vertices are D and E. The other 6 are odd. Now, a path is a sequence of vertices with the property that each vertex in the sequence is adjacent to the next one. The number of edges in the path is called the length of the path. So for example, if I am looking at a path from A to E, I would follow this edge, AD, and then follow this edge, DE. That is an example of a path from A to E. So from A to E, you can go A, D, E. And this path has a length of 2 because we had to travel along 2 edges. Now, for a non-example, B to G, that is not a path because there is no edge to follow along that. You could do B, F, G, but the path B to G is not a path. But BFG is. Now, a circuit is a path that starts and ends at the same vertex. So, for example, A to B to C back to A is a circuit. So if I say A to B to C and back to A. And again, you can talk about the length of a circuit and see that that has length 3. Going from G to F to H is not a circuit because you do not begin and end at the same vertex. Last set of vocabulary. We have a connected graph. Connected graphs are graphs where if you pick any two vertices, there is a path joining them. A graph that is not connected is called disconnected, and a disconnected graph is made up of separate connected components. So here in this first example, because there is no path from this vertex to this vertex, the graph is disconnected. We would say that this portion is component 1 because that whole chunk is connected. And this part of the graph is component 2. Now, in this second example of a disconnected graph, there are no edges. So there is no way to create a path between any two vertices. So this one technically has 4 components. Component 1, component 2, component 3, and component 4. Which leads us to our last vocabulary word, bridges. If you erase an edge in a connected graph that then makes the graph disconnected, then that edge is a bridge. So if we go back to this diagram here, which edges are bridges? Well, if I erased the edge GF, then the point G is isolated, so my graph is no longer connected. So that means that GF is a bridge. Similarly, if I erase HF, the point H becomes isolated, so that is a bridge. And lastly, if I erase edge BF, then this part, GFH, becomes isolated from the rest of the graph. So then I would have a disconnected graph. If you delete any other edge, it would not make the graph disconnected. So those are our only bridges. Now, the big concepts, Euler paths and Euler circuits. A path that passes through every edge of a graph is an Euler path. Edges can only be traveled once. So, in an Euler path, we travel along every edge of the graph once and only once. A disconnected graph cannot have an Euler path. But not every connected graph has an Euler path. This diagram is definitely connected, but there is no Euler path. If you don't believe me, you can go ahead and test it out. Pick a starting point. I'm going to start at R and see if I can travel on every edge. Not quite. I missed this one. I'm not going to keep trying, but if you think that I'm wrong, you can go ahead and try some more paths. But I promise you, there is no way to travel all of those edges exactly once. However, if I take this diagram and add one extra edge, I can create a graph that actually has several Euler paths. So let me see. I'm going to start at A. So if I go here, 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 I'm done. I traveled every edge exactly once. So for that one, I started at A, ended at L, and when I started, I went this way. Well, let's see if I can create another Euler path starting at A. Again, I have a different Euler path. Now, an Euler circuit, we already know what an Euler path is and we already know what a circuit is, so just put them together. An Euler circuit is a circuit that passes through every edge of a graph exactly once. Or you could say that it's an Euler path that starts and ends at the same vertex. This diagram here has several Euler circuits. So let me see. I'm going to start at R. So if I start at R, I should also end at R. Well, I started and ended at R and traveled across every vertex. So I have an Euler circuit. Not every vertex, every edge. Sorry. So I have an Euler circuit. So last thing is modeling. One of Euler's most important insights was that observations. All right, last thing we're going to take a look at is modeling. One of Euler's most important insights was the observation that certain types of problems can be rephrased as graph problems. So you can take a real-life situation and redraw it as a graph. It's one of the most important aspects of math. So if we go back to the bridges of Königsberg, we have this diagram of the city and the rivers and the bridges. You can model this with a graph. Each landmass is a vertex here. Each bridge counts as an edge. So you have two bridges here, one here, one over here, one over here. Take that out, and that's our graph. In fact, that's the graph that we were just looking at when I said this graph has no Euler path. We'll talk about why that is in the next video. A couple of other scenarios. After a rash of burglaries, a private security guard is hired to patrol the streets of the Sunnyside neighborhood. The security guard's assignment is to make an exhaustive patrol on foot throughout the entire neighborhood. Obviously, he doesn't want to walk more than he has to. His starting point is the southeast corner across from the school, so point S, where he has parked his car. And he wants to find an Euler circuit through the neighborhood. So you can redraw all of the roads as edges, all of the intersections are vertices. And he needs to walk along each edge exactly once and get back to his car. That's what he wants to figure out. Similar situation, a mail carrier has to deliver mail to the same Sunnyside neighborhood, but the difference between his graph and the security guard's route is that he has to make 2 passes through blocks where houses are on both sides of the street because he has to walk each side of the street. He only has to go once down a street where there's only houses on one side. And if there are no houses, he doesn't need to walk down that street at all. So this far side of the park, he doesn't need to go there. But we have put double edges to represent the streets where he has to walk down both sides of the street to deliver mail. So he could try to figure out the best route, starting from the post office, P, to walk through this neighborhood. Those are some real life examples that are legitimately used when businesses, post office, whoever, are trying to determine routes that need to be walked or driven or whatever. So we will learn about some theorems for graph theory in the next video.